right now. This is something we've been working on for a while now with my PhD student who's still at Columbia University, Camilo Hernández, who's actually going to move to London if there are possibilities to take planes. Like he's supposed to start at postdoc at Imperial in September, so you guys might be able to see him. Anyway, so let me tell you a little bit about our take on this, and then hopefully I will have time to show you what motivated us to start having a look at this type of problems and why we had to try and prove some things differently from what was accessible in the literature. So first, a quick example so that I can motivate a little bit what I want to tell you about. So this is something that most of you by now should be familiar with. This is what happens to you when you get invited to give a talk and you say that I have this very exciting thing I've been working on, but yeah, I don't have slides for that. So that means I have to prepare slides. So let's say you have a month, and well, the usual way it goes, at least for me, is that, yeah, obviously this is a month from now. I have plenty of time and many things to do. So I'm not going to start preparing the slides now. I'll just do that in 2 weeks. That's going to be good enough. After 2 weeks, well, strangely, as usual, the amount of things that I needed to do has not decreased. It usually increases. So yeah, well, I will still postpone again a little bit the preparation. So still have 2 weeks, it's fine. Same things happen after a week. I mean, a week is long, so why do it now? And then at the end of the day, you end up preparing your slides like at the last minute, or let's say the day before. That's not the case for this talk. I've already given it a couple of times now, so those slides were prepared before. But the message you want to take away from this, of course, besides the little joke, is that if you ask behavioral economists about how, say, standard human beings tend to discount the future, what they will tell you is that the way they do it is incompatible with the exponential discounting we tend to use in most of the control problem we look at. Okay, so let's see a little bit what happens if you try to get away from this this exponential discounting. Of course, there are a lot more other possibilities that create possibly time inconsistency in optimization problems. I'll mention them afterwards, but the guiding line in the talk is going to be non-exponential discounting. So that's the one I want to insist a little bit more on. Okay, so what I want to do here is control a state process. So I call it X, and I have my control new here, and so that the exposition in the talk remains as clear as possible, I don't want to tell you about what happens when you do volatility control. I'll tell you in the end what we can do in this case, which is for many of the the major results we have is we can still do it. It's just that writing things down becomes annoyingly technical, and it tends to hide like the overall message. So it's much easier for me to present this when you have only control on the drift. Okay, so I have this, and I have a reward functional. I have this running reward f, and I have a terminal reward capital F here, and the amount of utility that I get at some time t. This is the integral of this running reward and the terminal reward here. So the little twist compared to what you would usually have is that I have the current time t appearing here in the running reward and here in the terminal reward. Obviously, if you're familiar with standard control problem with exponential discounting, this is exactly the case, except that the t here appears as with an exponential that's multiplying this, and same thing here. The way you would try to address these problems would usually be to say, okay, I'm sitting at time t and I want to find the best control, that is to say the one, if there is any, that maximizes this criterion here. And the fact, what is good and what is powerful about Bellman optimality principle when it applies to such an optimization problem is that it tells you that doing the optimization from time 0 up until the end, or doing it from time 0 up to some intermediary time t, and then doing it again from time t onwards, give you exactly the same solution, right? That's exactly what you get when an optimal control is time consistent, is that you get the same solution for the optimization, whether you start at some time, at 0 or at some time t in the future. And unfortunately, this Bellman optimality principle, if I write a criterion like this, the only case where this is going to hold is if I have exponential discounting here. As soon as I depart from this, this is no longer true that Bellman optimality principle holds, which typically means that if I were to maximize this at time 0, and let's say that I find an optimal control for time 0, at any time t plus epsilon right after that, if I keep on following the optimal control of time 0, it's usually no longer optimal at that time t plus epsilon. So that means that just maximizing this criterion here may not necessarily be the best thing you can do. So the question becomes, when I have a reward functional like that and it's time inconsistent, typically for because of non-exponential discounting, what do I do with this? What is the problem I'm trying to solve? So there are maybe actually four answers to that question. It's just that there is one that, as far as I know, only makes a clear sense in discrete time. But in any case, so the solutions are, well, the first one is just say, okay, I don't want to solve that problem, and I'll just go back to exponential discounting. That's the easy way out, but as I said, if you want to be a little bit realistic sometimes about economic agents' behaviors, it might be interesting to have a look at what happens when you change the discount function. There is the second approach that I just mentioned, which is what usually is called pre-commitment, and that says that you're going to solve the problem at time 0 and assume that whomever is maximizing the criterion is pre-committed and is going to still decide to follow the optimizer you can find at time 0 here, even if at any later time it's usually suboptimal to do that. All right, so that's the pre-commitment strategy. It's by no means an easy problem to solve. Again, you're trying to solve this maximization, but there is no Bellman optimality principle, so it's extremely unclear what you should do and how you can try to tackle that problem. There is a huge literature here. I'm not mentioning, this is not comprehensive at all here, what I'm showing, but it's just that there is this recent paper by Karnam and Zhang, where they show that you have general techniques that allow you to construct a time-consistent problem, which has the same value at time 0 as this one. And if you're able to do this, of course, then you can at least compute the value, because you just compute the value of the equivalent time-consistent problem. The question becomes usually how to construct this equivalent time-consistent problem, and that can become very complicated. So this is not the road we want to follow. Well, the road we want to follow is one that has a more game theoretic flavor, and this is these equilibrium that I'm going to talk about now. They've been introduced, I think, for the first time in the 40s or the 50s. And the idea is just to say that what you want to do is some sort of no regret strategy, where when you implement that one, even if at time 0, of course, this is usually suboptimal because you're not maximizing anymore. At the very least, there will be no incentives for you at any point in time to deviate from that equilibrium. All right. So the way to see this, one way to see this is that you have basically a game, and the game is being played between you and your future incarnations. And what you're trying to do is some sort of Nash or, let's say, Stackelberg equilibrium between you and your future selves, so that when we are playing this equilibrium, none of the players, meaning none of your future incarnations, will have any interest in deviating. All right. So again, extremely huge literature on this in discrete and in continuous time as well. So I'm not going to list everyone here, but just insisting that this is the road we're deciding to take here, and that's what we want to study a little bit more. So I gave you this somehow abstract definition of an equilibrium that was not really clear. So let me describe a little bit what happens if you try to do this in discrete time. And then I'll try to justify why we move to continuous time. But discrete time, it's, as usual, much clearer and much easier to see what's going on. So how do you do this? When you have standard optimal control problems in discrete time, a very good tool is to think with backward induction, right? You start from the end and you try to go backwards in time. So let's try to do the same reasoning here. So let's assume that I can only choose my controls on a given fixed time grid here, and that I am at time tn minus 1, and all the previous players, that is all my previous incarnations, have already made a choice. The last player, given that what everybody has done, has just a standard optimization problem to solve. So let's say that we can do that, and you have some sort of optimal, some sort of best reaction function of player tn minus 1, given what everybody else has played before. So I do this now. What happens if I want to go back one step? If you want to come back one step, then what you have is a Stackelberg equilibrium between player tn minus 2 and player tn minus 1. And why is that? This is Stackelberg because player tn minus 2 plays first, and player tn minus 2 does the following reasoning. Okay, let's assume that I play this control, this strategy between tn minus 2 and tn minus 1. Then I will anticipate what will be the reaction to this of player tn minus 1 that's going to control the system between tn minus 1 and capital T. And in order to optimize his own criterion, player tn minus 2 takes in feedback form whatever best response player tn minus 1 had. So this is typically what you do when you have a Stackelberg equilibrium. And if you can solve that problem, you can come back one step. The obvious difference with the case where you would have time consistency is that player tn minus 2 actually doesn't really care about what player tn minus 1 will do, because it is enough for player tn minus 2 to just solve his own optimization problem between tn minus 2 and tn minus 1. That's exactly what dynamic programming tells you, that you can solve those problems independently and then paste them together in the end. Okay, so let's say that I can do that construction and iterate, and that at each step I have to solve these Stackelberg equilibria that are going to stack up on top of each of them. If I can do this by construction, I will get an equilibrium. All right, so that would be exactly something where when the first player plays it, and all the other ones are going to follow the equilibrium because they have no interest in deviating. Of course, the hard question is whether, I mean, the first one here is something that you can usually solve. It's standard optimization. If you have a little bit of concavity or convexity, this is going to work out. This iteration here tends to stop working very fast. If you look at one of the most important papers when you go to continuous time formulations of those problems, which is by Eklund and Lazrak, this is exactly what they say there, is that they wanted to go to continuous time because even if in discrete time you can make sense of the definitions relatively easily, it is extremely hard in general to prove that an equilibrium exists, even if you would have in principle this backward algorithm to construct them. Another important point, just imagine that you want to do the same thing in discrete time, but with infinite horizon here. Then I don't even know how to do the construction, right? Because I would have to start from infinity and go backwards. So what's happening here? Does it mean that in order to construct the equilibrium, I have to fix some sort of fake terminal time and then let this go to plus infinity? It becomes very unclear what you're even doing there. So because you, in general, cannot really say anything about those equilibria in general discrete time models. You may want to move to continuous time. But if you want to move to continuous time, then it starts becoming complicated to actually just define what you mean by an equilibrium. So maybe let me explain this the following way. An equilibrium would be that I have all my players. So when I'm in continuous time, because I can control the system at any time between, say, T0 and capital T, I have uncountably many players that are indexed by any points in time between 0 and capital T. And when I say that an equilibrium is a strategy such that no player has any interest in deviating, that means that if I have player T, the one that chooses the control at time T, if he deviates, then he's not getting more in terms of rewards. And now just have a look at the reward I was considering. If at some time T here, I change my control, I have a nice Lebesgue integral here. I'm changing the control on a set of Lebesgue measure 0 that has absolutely no impact on the criterion here. So already just presenting it that way means that you cannot have a naive generalization of what's going on in discrete time. And that's why there is also a much more developed literature of optimal stopping, like time-inconsistent optimal stopping in continuous time, because when it comes to optimal stopping, when player at times t decides to impact the system, he decides whether to stop or whether to continue, this clearly has an impact on the system itself. So there it's much easier in some sense to define the notion of equilibrium. It's not much easier to solve the problems afterwards, but just the definition is more natural. So the definition I'm going to show you, this is the one that's mostly used in the literature. That was the one introduced by Eklund and Lazrak. And let's see what they're saying here. So basically, they say that a control is an equilibrium if. So forget for 1 minute the lim-inf here, forget the division by L. Let's just look at what's going on here. They say that something is an equilibrium if I compare the reward I get at time t for player t when following the equilibrium. I compare this to the reward I would get at time t, being player t, and following an alternative control. And what is this alternative control? You have this L here, and the alternative control just changes to an arbitrary control nu between t and t plus L, and then reverts back after L to the optimal control, to the equilibrium. Then you want this difference to be positive. All right, that sounds good. That just means that you have no interest in deviating. But here what you're doing, you're not really deviating at time t. You're deviating over a small window of time between t and t plus L. So the game theoretic interpretation of this usually is that they present it in a way that you and your future selves between t and t plus L enter into a coalition, and you all agree to deviate to this arbitrary control here. All right, so then maybe something you want to say there is that I do these coalitions, I look at the sign, and then I will let the size, the length of that coalition go to 0, right? Because I want to have something that is saying that things are working locally. So that's when you would take the lim-inf, and you take the lim-inf because you don't know whether the limit exists or not. Very good. So why do you have this divided by L here? Well, the point is that imagine for an instant that your reward J is a little bit regular, so you have a little bit of continuity at least, and you take controls here that say are continuous in time. And typically, if you look at the limit of this minus this, when L goes to 0 without dividing by L, this goes to 0. Like you just need a little bit of continuity for this to hold. So of course, if it's the case, then asking that the limit of this minus this is greater or equal to 0, that doesn't give me any information if the limit is typically 0. So that's why you divide here and you basically go to the first order and ask that this non-trivial limit has the sign that you want. Okay, so that's the reasoning behind the definition. And okay, so when I say not completely satisfying when lim-inf is 0, of course, this is because if the lim-inf is 0, you could very well have that the lim-inf is attained through a sequence such that this quantity is strictly negative for any L and is just equal to 0 at the limit. All right, so that would mean that, well, along that equilibrium, actually, you would be better off by deviating all the time, except when you are exactly at time t, because then here you get 0. But what's happening in actually is that you are better off deviating, but the amount of utility that you get by deviating is arbitrarily small. So that means that in the case lim-inf equals 0 here, the definition that you have is not an equilibrium, it's some sort of epsilon equilibrium. All right? I'm saying that because we're going to tweak the definition a little bit and write it more in that spirit. So the only thing that bothered us when we were trying to use that definition is that what you want to say is that this condition is locally telling you that nu star is optimal. All right, and it wants to tell you that basically over any small coalition, right? You take a coalition, it's very small, but it's always, I mean, it's never better for you to deviate when you are between that window of time from nu star to something else. That's what at least I would like the definition to tell me. And because you're taking a lim-inf here, this is just a little bit annoying because your lim-inf is attained along a sequence. So that means that maybe you just have countably many points at which this is, you have this property. So I don't really like that. So I'm going to reinforce the definition a little bit and just transform it. In spirit, it's exactly the same thing. It's just a different way of writing it. And it's just that that one is more convenient for what we're doing afterwards. So for us, an equilibrium will be exactly what I told you. So something is an equilibrium, actually an epsilon equilibrium, if for any epsilon, I can find some L epsilon, such that if I do the same game and I deviate between t and t plus tau, where tau is less than this L epsilon, best case scenario, if I deviate, I gain epsilon times tau, and the multiplication by tau comes from the multiplication by the size here. Okay, so it's reinforcing a little bit because the lim-inf wouldn't tell you that this holds for any tau less than L epsilon. It would tell you that this holds along a sequence there. So I'm just reinforcing that a little bit and write it that way. But again, don't want to say that we're inventing anything. It's just a convenient rewriting and reinforcement of the definition. And there is also from this something you can easily see, which is what I will call a strict equilibrium, which will be the ones for which the L epsilon here can be taken uniformly over epsilon, in which case I can let epsilon go to 0 here, and I would have an actual equilibrium and not just an epsilon one. It's easy to just describe both of them with that definition. All right, so that's exactly everything I told you. Those strict equilibria, they are nice. I mean, in general, you would like for them to exist, but you shouldn't be too optimistic about it. And what we are able to show and what other people were able to show is that typically the ones that exist are the epsilon equilibria, not necessarily the strict ones. And everything I'm going to tell you characterizes only the epsilon ones, right? But there are recent results by Huang and Zhu, where they work with continuous time Markov chains. And there you can actually say a lot more about when an equilibrium is strict or is not strict. But yeah, I don't have much to say about that. I just wanted to mention this. Okay, so what do I do with this? If you look at the literature, I mean, besides what I just showed you with this modification of the definition, people wanted to go to continuous time because, as usual, you hope that it's going to be easier to solve problems. So one of the, there are a series of 2 or 3 papers by Ekland, Lazrak, and Pirvu, where they showed that it is possible to introduce what they coined an extended Hamilton-Jacobi-Bellman equation, which characterizes somehow those equilibria. And if you are familiar with standard optimal control, in standard optimal control, you can do verification arguments. I give you the optimal control problem. You can write down immediately the Hamilton-Jacobi-Bellman equation associated to it. And you know that if you are able to find a smooth solution to that Hamilton-Jacobi-Bellman equation, it's usually going to coincide with the value function of your optimal control problem, and it's going to allow you to identify an optimal control. So what they did in a specific example is show that there was some sort of extension of this. So this is a system, actually an infinite dimensional system of PDEs, that if you can find a smooth solution to it, then you get exactly the same reasoning. You have a verification, and you have that allows you to construct an equilibrium. This was largely extended in a series of papers by Bjork, Kapko, and Murgochi to basically any general Markovian diffusion you want. And they explain, so that part is the part that's not a rigorous statement, but they show intuitively how the extended HJB equation arises in those problems, and they prove a verification result that says exactly what I said. If you can find a smooth solution to the system, you're good to go and you construct an equilibrium. Okay, so that's good, but that leaves, at least when I was reading all of this, that left 2 points that were actually important for the applications that I had in mind and that could not be addressed with what was done there. The first one, it's a little bit technical, but it's about non-Markovian versions of this. And as you will see, if I have time to show you the application in contract theory that I have in mind, doing non-Markovian case is not just for the sake of doing it, is just something that is inherent to the problem that I have, and I cannot not assume that things are non-Markovian. You will see in those contract theory problems, you have to be able to understand the non-Markovian version of the problem. So that's one thing, maybe not the most important, that's really related to my application. The other one might be a little bit deeper in the following sense. If you are familiar with standard optimal control, you will know that the way you go at it is usually the following. Of course, you have the the cases where you're very lucky and you can find smooth solution to the HJB equation. But typically, this is not the case. And it's very easy to construct examples where HJB equation doesn't have a smooth solution. So the way you go at it usually is you prove that dynamic programming principle holds for your problem. And using dynamic programming principle, you can at least show that the value function is a viscosity solution to the Hamilton-Jacobi-Bellman equation. And then if you have uniqueness result for that PDE, then you have a characterization of the value function at least. And then from there, you can start and try to work a little bit more and hope that you get some enough regularity, say, so that you can make sense of the optimal control. It's more on a case-by-case basis. But at the very least, you have that direction where you say, okay, I have DPP, and the DPP shows me that the value function is necessarily related to that Hamilton-Jacobi-Bellman equation. We're missing that direction in the time-inconsistent case. I know that if I have a solution, smooth solution to the extended HJB equation, that allows me to get the value along an equilibrium and to identify the equilibrium. But I don't have anything that goes the other way around. And if I want to have something that goes the other way around, I need to have some sort of dynamic programming principle. So you might be wondering, okay, why is he talking about dynamic programming principle in a time-inconsistent setting if he said in the beginning that it did not hold? What you should actually realize is that an equilibrium, one way to describe it, and I'm taking this from a paper, but I don't remember which one. I think it's a paper by Pollack. A time-inconsistent, an equilibrium is a time-consistent strategy for a time-inconsistent problem. And because the equilibrium is a time-consistent strategy, because somehow you have no reason to deviate from it, then there should be some sort of dynamic programming principle associated to it. Okay, that makes sense. So now you try to think about this. You look at those papers by Björk, Kapko, and Mergoshi. They did one paper in discrete time where they have something like that, some sort of dynamic programming, one period one that they can iterate that appears. And if you look at their paper in continuous time, it's a little bit hidden, but there is also a dynamic programming principle appearing there. And the way they get it is they basically say, look, imagine I have a smooth solution to that extended HJB equation I showed you. I mean, that they have. I haven't showed this to you yet. So imagine I have a smooth solution there. I can play a little bit, apply Ito's formula, and I can actually find a time-consistent problem, which has the same value as my time-inconsistent one, and such that the optimal control in the time-consistent problem is an equilibrium in the time-consistent one, the time-inconsistent one. So you think, okay, that's great, that's magical, this is exactly what I want, because then the dynamic programming principle that we know holds for the time-inconsistent problem, for the time-consistent problem that I just identified, is going to give me a dynamic programming principle for my equilibrium in the time-inconsistent problem. True, there are two things that are a little bit problematic with this. One is that in order to construct the equivalent time-consistent problem, I need to know what the equilibrium is. All right, and of course, if I already knew what an equilibrium is, I wouldn't need to talk so much about all of this. So that's one issue. And the second one that is more problematic for me is that even if you're happy with the result that they have, they prove it by assuming that this extended HJB equation has a smooth solution. And as I told you, this is already a lot if I want to get general result in standard optimal control. So I should be very careful with making assumptions like that if I want to work in a general setting for time inconsistent. So, and also somehow it would be just be satisfied with that result would be as if in standard optimal control problem, I would tell you that you're happy to prove the dynamic programming principle by saying, I assume HJB equation as a smooth solution, and I deduce dynamic programming principle from that. You can do it, of course, that works, but you would rather prove dynamic programming principle from first principles rather than going to the HJB and then going back. All right. So that's what was motivating us a little bit to try and understand a bit more how this works. And well, I'm going to, move a little bit faster, but basically we proved the dynamic programming principle that they were showing in their previous papers, but without having to say anything about the HJB extended system in a completely non-Markovian setting. It's like a proof that is reminiscent of the one you would do if you were just doing standard control. So let me just show you how this intuitively works. But the point I was telling you is that when you have an equilibrium with our definition, this is locally optimal, and using that equilibrium typically allows you to get something up to losing this epsilon L epsilon that's coming from the definition here. All right, so this is something I could do and pushing this for any time tau that's less than L epsilon. All right, but dynamic programming principle is not like that. I would be able to push this for any time tau between 0 and capital T. So the way to do it is that you iterate. Instead of doing this between 0 and L epsilon, you do it between 0 and L epsilon, and then between L epsilon and 2 L epsilon. So you keep on doing it, and you can go as far as you want that way. And then you're going to start accumulating those epsilons, L epsilons here. And then you hope that when you let epsilon go to 0 in those iterated dynamic programming principles here, which are similar to the one period one I was mentioning, you hope that when you let epsilon go to 0, this makes sense and things work. Well, that's the proof. I mean, that's the where you have to work somehow a little bit, but it works, and you obtain exactly what they have, which is the following form of the dynamic programming principle. That is, your value along an equilibrium satisfies that this is the soup over all other possible controls of the value at any arbitrary later time here. So that's what you would get typically for dynamic programming. Then you get your running reward. So notice here that the running reward is along the diagonal. I had this 2 times and I get the diagonal. So if I had a time consistent problem, I would stop here. That would be exactly the dynamic programming principle for my problem. And because I have time inconsistency, I get 2 additional correction terms that come from derivative with respect to this time variable of the terminal reward here and the running reward here. And as I mentioned, the dynamic programming principle makes the optimal, the equilibrium appear here. It doesn't appear here. This is any alternative control you're choosing here. But when you go there, you have to plug in the equilibrium. I mean, of course, we're proving the same result as the one that they had. So it's going to look the same, and you're going to have the same issue with what's going on here. All right, but then once you've been able to do that, and you didn't have to rely on any PDE argument or anything, this is great, because once you're here, you can start using the typical tools you were using before for optimal control. And at this stage, what you're using is the so-called martingale optimality principle, which is telling you...
Sorry, Dylan, I think there's a question from Martin.
Yes.
Yeah, when you do this, putting this mesh size together, but is this uniform in epsilon? So is, because I mean, you go to L epsilon and then the...
So, I mean, it's not straightforward to pass to the limit. Like, you really have to take care of the terms and make sure that things are not going to diverge. So you have the L epsilon, the way we define it is a little bit different from what I've written. You just define it in such a way that is monotone with respect to epsilon. That's very easy to do. And then you know that L epsilon, because it's monotone, it has a limit. And you have to work depending on whether the limit is 0 or whether it's strictly positive, and just play around with all of that. And in the end, you can get that this actually converges to this. So you need assumptions. It's not completely for free. I need typically to assume that my rewards are maybe continuous with respect to state and things like that. But you can do it.
Thank you.
Yeah. And also for the last term, this partial derivatives with respect to which variable?
So this is with respect to the added one, so the one that corresponds what I would usually call type. So if you had exponential discounting, this here would be derivative with respect to the just the exponential part, not the rewards themselves.
Okay. Thank you. Yeah.
So once you're there, as I said, you have this martingale optimality principle, and it tells you that when you look at the dynamic version of this, where you have conditional expectations, then the value should typically be a super martingale when you choose an arbitrary control, and it's a martingale when you choose the best one. If you're familiar with this and you've done this in non-Markovian settings, you know that this is how you can characterize the value of optimal control problems with drift control only by BSDEs. And well, same thing happens in this setting. What you get is this somehow a little bit weird system of BSDEs that shows up. So yeah, I mean, I've been speaking a lot, so I don't have that much time to explain, but basically if you're familiar with this, you look at the first line, this would be exactly the backward stochastic differential equation you would write for the optimal control problem I showed you in the beginning, with the following caveats. So this H here is the Hamiltonian. The generator of the BSDE is the maximization of the Hamiltonian. That's completely standard. I have this weird term here, but think about it for 1 second. If I have exponential discounting, typically I would have a linear term here multiplying this y guy, and I would have just that one nice equation that would be standard optimal control. In the time inconsistent case, instead of having the nice linear term in this y coming from the exponential discounting, I have something a little bit more annoying to deal with. So this is partial YRR. So what is this? Well, I have another equation, which is this YTS, which more or less is a derivative with respect to this variable of the first equation, evaluated along a maximizer of my Hamiltonian. So this is what somehow is taking care of the fact that here the maximizer appears. And what do I need to do here? I need to differentiate this with respect to this parameter, and then I need to evaluate this along the diagonal and plug it here. So what I have is some sort of infinite dimensional system because I have this one equation, which is coupled with infinitely many of them here, because this guy here is indexed between 0 and capital T completely. But this is exactly the system that shows up if you try to do the analysis. And this is exactly the, if you want, probabilistic representation of the extended Hamilton-Jacobi-Bellman equation if I specialize to the Markovian case. So what can I do with this system? I can do the following things. I can do the verification, and I can do the other direction that I liked. If I have an equilibrium, if you give me one, I can show you that this equilibrium has to arise from a solution to my system, because if you give me an equilibrium, I can always construct a solution to this BSDE system, and this equilibrium has to be equal to a maximizer of my Hamiltonian here, evaluated along a solution to this system. So that's exactly the same statement as the one you would have in standard control problems. If I control the drift only, I can show you that if something is an optimal control, I can construct a solution to this BSDE, just the first one, and that the optimal control has to be a maximizer here. So that's exact equivalent of a result in optimal control. I, of course, have a verification, and my verification tells you that if you have a sufficiently integrable solution to the BSDE system, then this guy is an equilibrium, and the value along the equilibrium is given by the first component of the solution. So that's the same verification result that people had before in the literature, except that it's extended to the non-Markovian case now. Yeah. I also can show that I have wellposedness for the BSDE system, and it's actually relatively easy to prove. Just assume that basically everything is Lipschitz and everything is sufficiently integrable, and you can use the standard Picard iteration or Banach fixed point arguments to prove that the system has a solution. So this is not the first result of its kind, because there is another paper, PDE-like, where they prove that in the case of drift control only, the PDE has a smooth solution. So typically, the results that you get using BSDE are a little bit better in terms of assumptions, simply because if you want to think about PDEs and the ones that appear in standard optimal control, when you control drift only, the PDE associated is a semi-linear PDE for which you have a very well-developed theory of Sobolev solutions. And the BSDEs are somehow exactly that. They're exactly the Sobolev solutions to the PDE system. So what we have here is somehow something similar, that it's relatively easy to get those Sobolev solutions of the extended Hamilton-Jacobi-Bellman equation. And it's typically a little bit harder to get existence of classical solutions. But okay, when you control drift, again, The difference is not that huge. It's just that I am biased with probabilistic arguments compared to PDE ones. But yeah, I mean, at least you get all of this going on here. Very good. So that's the whole story somehow in the drift control case. Let me tell you a little bit more how much we know how to generalize all of this. So what happens if I control the volatility? If I control the volatility, the proof of the dynamic programming principle stays the same. So that doesn't matter whether you control drift or not. We can do it without any problem. The proof of the verification result still holds as well, except that now what is going to characterize your value and your equilibrium is some sort of second order BSDE system. What we don't have, and what, as far as I know, no one has in a general setting, is a wellposedness result for this 2 BSDE system when the volatility is controlled. And I mean, I don't want to go into the technical details why this is much harder, but I really have very little clue about how one could go at it in a general setting, simply because the way the definition is currently written here, there is something that, unless you have a lot of regularity, you shouldn't be able to have. So I'm not saying that this is useless when you go to the controlled volatility case. The point that I want to make is that what you need here is existence of the equilibrium, right? Because you need the equilibrium to state and to write the system. When you have a standard control problem, when you control the drift only, existence of the optimal control is okay. As I mentioned before, this is something you can easily prove. If you want to go to general control problems where the volatility is controlled, the only general statements that I can make are existence not of an optimal control, but existence of a relaxed optimal control. Right? And this is when you start going into randomization of controls and you're not playing controls anymore, you're playing measures over the set of controls. If I go there, I can have a general statement that tells me that a relaxed optimal control will exist. If I'm lucky and you use like those so-called Filipov conditions, then sometimes you can construct a non-randomized optimal control from the randomized one. But in order to do all of this, you need to randomize everything. So my point here is that because in the statement of this 2 BSDE system, I need the optimal control to exist. I mean, the equilibrium, which is the equivalent of the optimal control, it shouldn't come as a surprise that it's very hard to do it the way we were trying to do it first. And that probably the way to go at it, what at least we think we should be doing and we're trying to do, is to write down relaxed versions of everything I showed you, try to prove that everything works in the relaxed framework, and maybe try then using similar to those Filipov conditions and get existence of an equilibrium. But it shouldn't work directly like that, because this is just a fundamentally hard problem that we don't really know how to solve in the standard control case. So it's even more unlikely that we know how to solve it generally in the time-inconsistent case, right? So, I mean, that can also be seen as an excuse of like, we just don't know how to do it. But there are reasons why this is significantly harder than the drift control case. Something that I mentioned in the beginning, of course, having here the non-exponential discounting, this is not the only way you get time inconsistency. When you do finance, one of the typical cases would be mean variance. If you have mean variance like criteria, then you typically get time inconsistent problem. So we can also deal with that. This form of the criterion, this is the general form from this paper by Björk and Myogoshi, where you just add here a nonlinear functional of this conditional expectation, which typically allows you to treat mean variance problems. We know how to deal with that. And again, you get the whole thing with the DPP that still holds, verification still holds, except that now you typically have a system of 3 coupled equations instead of the 2 ones that I showed, even if the system is still infinite dimensional. All right, so that still works, and the proofs are not harder when you do it that way. They're just a little bit more annoying to write because of notations. All right. Yeah, maybe I'm not going to have time to show you how to solve the problem, but let me try to motivate just a tiny bit. The 2 points I was mentioning were important for me, and they come from applications in contract theory. So contract theory here, I'm going to have to go a little bit fast, but this would be a setting where you have a principal. Principal wants to hire an agent, and the agent is managing a task, and the value associated to this task is this X. The way the agent manages it is by choosing the control alpha here, and the principal observes X, but doesn't observe alpha, and he wants to try to pay the agent contingently only on his observation, meaning contingently on his observation of X. So if the principal rewards the agent at time capital T with this salary, right? So this is something that depends on the observation of X. So a priori on here the path of X. I assume that I have a very simple agent and that is risk neutral. It has quadratic cost, but it has non-exponential discounting, right? It discounts the future with some function f here that doesn't have to be exponential. So that means that the criterion of the agent is time inconsistent. So this is here that you see that for that problem, because the contract is non-Markovian, I need to understand what to do with non-Markovian problems. And it's not just me telling you, yes, the contract has to be non-Markovian, but actually maybe taking it Markovian could be enough. We solved that problem, and the optimal contract is non-Markovian. So you have to take it non-Markovian here in those problems. There is really no way out of it. And typically, even in cases where the agent would have a time-consistent criterion, the optimal contract, this is something we worked on with Nizartuzi and Yaksha-Zvitanic, the typical optimal contract is a non-Markovian function of X. So really no way out of this here. So that's one justification why, okay, I need to do things in a non-Markovian context. My other important point was that I needed what can be seen as some sort of necessity condition, in the sense that if you give me an equilibrium, if you tell me it exists, I wanted to be able to say that this equilibrium had to come from something, from the extended Hamilton-Jacobi-Bellman equation, from this BSDE system that I showed you, but I wanted to be able to have a statement like that, which, as I mentioned, was lacking from the literature, because the only cases where you had something a little bit similar were ones where you had to assume that the extended HJB system had a smooth solution, which I really cannot do in applications like that. I mean, especially because here I actually had, this is non-Markovian, so I don't even have the PDE system. And why do I need that? That's because in those problems, the way you think about it is the following. The principal is offering a contract to the agent, and the typical assumptions that you make there is that because the principal is offering a contract to the agent, he will never offer a contract for which there is no, at least not, for which there is not at least one equilibrium. Why? Because if there is not at least one equilibrium, then you don't know what the agent is doing. So you cannot compute the best reaction function of the agent, and you cannot solve the problem of the principal, which in the setting is either something you call a bi-level optimization problem or a Stackelberg equilibrium, if you're more inclined to game theory. And that's exactly what is done in the standard setting. So that's the natural extension here. So that means that for me, in this problem, what I should start with is say, okay, principal offers a contract to the agent. And admissibility of this contract is that there must be at least one equilibrium for the agent. Then this is where my result becomes important, because you tell me now, yes, there is an equilibrium. I know how to characterize it. It comes from my BSDE system, which here is written exactly with the specifications of that simple example. So that's where I need this type of results. And those results were not available in the literature before. Okay, so maybe just skip all of this. This is how you can solve it. And let me just show you the optimal contract so that you should be agreeing with me that it is typically non-Markovian. So what the optimal contract looks like is, this is a constant. And here you have this integral with respect to dx. So this is a nice integral. It's Gaussian because this is a nice deterministic function. But it's non-Markovian. It clearly depends on the whole trajectory of x here. And of course, if f is exponential discounting, this here is a constant. It goes out, and the optimal contract depends only on x capital T and becomes Markovian. But that only happens in that example when you have exponential discounting. As soon as I change it, this is non-Markovian. And okay, if you want, that justifies a little bit what I was showing you. So just to conclude, this is just one example that we managed to solve. There are a couple more we know how to solve. We're still a little bit stuck on figuring out what is the general strategy to solve these principal agent problems when at least the agent has time inconsistent preferences. And I didn't have time to mention that, but this is intrinsically linked to weird optimal control problems involving forward Volterra equations. But yeah, I don't have time to go into details here. That's just so that I could justify part of the title I sent you. And yes, I will stop here. Thank you.